Hi, this is Sir Aris. Let us talk about Chapter 2, First Order Differential Equations. The general form for first order differential equations is given by this expression, and our goal is to develop methods for finding a solution. Generally, it would be very difficult to look for one method to find or the ultimate method to find the solution. So we will consider finding methods applicable to a certain subclass of first order equations. That includes linear equations, separable equations, and exact equations. First, linear equations. These are functions that if the function f depends linearly on y, then the differential equation dy dt equals f is a first order linear equation. For example, this expression dy by dt equals minus ay plus b, where a and b are constants. The general first order linear equation can be written in this standard form, where p and g are given functions of the independent variable t. This equation can also be written in a convenient form pt dy by dt plus qt y equals gt, where p, q, and g are given. Let's try an example. Solve the differential equation 4 plus t squared d derivative of y with respect to t plus 2ty equals 4t. The left side of the equation can be written as derivative with respect to t of 4 plus t squared quantity times y. That can be easily checked. So if we apply this the derivative of this product of two functions, you get 4 plus t squared times dy by dt plus 2t, this one, 2 times t times y. Our differential equation, we have simplified the left side. That's equal to the 4t on the original form, the original equation. Integrating both sides, we have 4 plus t squared times a quantity times y equals 2t squared plus c, where c is a constant. Solving for y, we can write it like this. Let's try to solve equations using a specified method. Since most first order linear equations cannot be easily solved just like in the previous example, we try a method, this is due to Leibniz, to multiply the differential equation by a function mu of the variable t. This mu is called the integrating factor. Let's try an example. Given this differential equation, we draw some representative integral curves. That is the plot of solutions for different constant c. Also find the particular solution whose graph contains the point 0, time equals 0, and y equals 1. Our first step is to multiply the equation by the integrating factor mu t. And then we choose a function mu of t so that the left side can be written as the derivative of mu t times y, or that is written in the left side of this equation. Expanding, we get mu t times derivative of y with respect to t plus derivative of mu with respect to time, with respect to variable t times y. Now, if you compare from the original equation, differential equation, and this equation, we find that this term here, 1/2 mu times y, and derivative of mu with respect to t times y gives us that the derivative of mu with respect to time is equal to 1/2 of mu of t. Dividing both sides by mu, we get that this expression can be written as derivative of ln mu t equals 1/2. Integrating, we get ln of mu equal to 1/2 t plus constant capital letter C, or we can write mu exponentiating both sides equal to constant small letter c times e to the power of t over 2. This mu is our integrating factor. And for this case, we can set c to be any value, let's say 1 for convenience. And here we have chosen our mu to be equal to e to the power of t over 2. So let's go back to our main problem, multiply the differential equation by mu. We get this expression. So we can write the left side as a simple in a shorter form like this. Okay, the other side, we can combine t over 2 and t over 3. That becomes 5t over 6. Integrating both sides, we get this term equal to 3 over 5 e to the power of 5t over 6. And c here, plus c. C is an arbitrary constant. Solving for y, we get the general solution. For values of t and y, 0 and 1 respectively, so we set t to 0, okay, and y to 1, we get c as 1 minus 3 over 5, that's 2 over 5. The plot for the direction field and integral curves of the differential equation is shown here. The short lines correspond to the slopes or the direction field, while the solid blue lines are the integral curves or the solutions for this expression, this differential equation, which is this equation for different values of c. The black curve here corresponds to the point, to the solution passing through 0, 1, or when t equals 0 and y equals 1, that gives c equals 2 over 5. Let's have another illustration. This time it's a little bit general, in a sense that we have a general expression g and a function or a constant we call a. We multiply both sides by mu, and we're using our method of writing the left side as derivative of mu times, so there's a missing y over here. Okay, so that we get mu t dy by dt plus d mu t by dt times y. The integrating factor must then satisfy this expression, so that this term here is equal to this a mu t. Dividing both sides by mu, we get, then integrating, we get mu equals e to the power of a t. Multiplying that integrating factor to our differential equation, we get this simple form on the left side. Integrating, we get this e to the power of at times y equals the integral of this term. We write it simply as the integral plus arbitrary constant c. Writing for y, we get e equals e to the minus at, and setting the integration limits t sub 0 to be any convenient choice, and t we set as general value of t. To avoid confusion on the integrating variables here, originally we call it t, and the limit t, we replace the variable t inside the integral as s. So after integrating, we just then get back the variable t. Okay, this is the general form for the solution given by uh, that general, uh, slightly general differential equation. For as an exercise, please include examples 3, 4, and 5 from chapter 2.1 in your handwritten notes. Okay, the next method, it's called separable methods of finding differential equations by separating the variables. We call it method of separable equations. The general first order equation can be written as this form, where m and n are functions of x and y. We consider a subclass of first order equations where m is a function of x only and n is a function of y only. So we write here m of x and n of y. Such equation is said to be separable, and we can write it in a form mx dx plus ny dy. This has advantages. First is that the terms involving each variable may be placed on opposite sides. So we put on one side variables related to x, and on the other side, or on one side, variables containing only x, or terms containing only variable x. On the right side, we can put this term containing variables only, or only y variables. And we can also suppress the distinction between independent and dependent variables. So it won't matter whether we choose x or y as the independent variable. For example, show that this equation is separable and then find an equation for its integral curves. Since we can write it in this form, it means that it is separable. This is a function of x only. This term here is a function of y only. The second term here can be written as the derivative with respect to x of, with respect to x of y minus y cubed over 3, considering that y is a function of x. The differential equation then can be written as, so here are x from this term here, we write it as the derivative of x cubed over, or the negative x cubed over 3. The derivative of that is simply x squared. Here, the derivative of this term gets us back this. Or that equation we can rewrite as derivative with respect to x of minus x cubed over 3 plus y minus y cubed over 3. Integrating, we obtain minus x cubed plus 3y minus y cubed equals constant c. The integral curves are shown in the solid blue lines. The short lines are still the direction fields, or the slopes of the expression for y. In a different way, we can write directly the differential equation. This is still the same example, but we rewrite the equation in this form so that y variables are on the left side, x variables on the right side. Integrating the left with respect to y and the right side with respect to x, we then get this term where we add the integration constant c1 for the integration on y, and C2 for the integration on x, or on the right side. So we can combine the C1 and C2. We can also multiply both sides by 3. We get this form. Now let's move to a different example. Let's consider this equation, differential equation. There's a boundary condition that at time t equals 0, y equals -1. We want to know the we want to determine the interval in which the solution exists. Before we proceed, we can see here that y should not be equal to 1. Okay, so just keep that in mind. The differential equation we can write by separating the variables involving y, and on the other side, the forms or the terms containing only variables x. Integrating, we get here y squared minus 2y. So there's a term 2 here. This part becomes 3x squared. That becomes 3x cubed over 3. So 3 cancels out. 4x squared over 2. So 4 divided by 2 is 2. And 2x plus constant of integration c. For x equals 0 and y equals -1, let me go back to the previous slide. So x being 0 and y 1. So this is 1 minus 2. That y minus 2 times -1, that's 3. All of this are 0, so c equals 3. We can write this expression for our solution. This is the final form of our solution, but it's written implicitly. If we want to write it explicitly for y, we move this term to the left side of the equation, becomes negative of this term. Now this becomes a quadratic equation in y. So y squared, this is the coefficient here is 1. Here the coefficient is -2. And here the coefficient is negative of this quantity. Using the quadratic formula, we get the value for y as -2b. So this is 2b, or 2 times or negative b, or negative b. So that's negative or positive 2 y minus or plus and minus square root of negative b, or b squared, which is -2 squared, minus 4. A is 1, c is negative of this quantity, divided by 2a, 2 and a is 1. So distributing this 2, or 1/2, from the 2 in the denominator to the 2 terms, so the 2 here and 2 cancels. You have 1 plus and minus square root of, we put 1/2 on inside the square root. You have, that becomes 1/4. So the 4 here cancels with 1/4, minus the 4 also cancels with 4. And we are left with plus x cubed plus 2x squared plus 2x plus 3. 1 and 3 adds up to 4. If we recall our boundary conditions, we set x equals 0. We should get a value of y equal to -1. So since here we have two choices, whether the sign is positive or negative, to resolve that, we simply use our boundary conditions. If we set x to 0, all of this becomes 0. So we get square root of 4, that's 2. If we choose positive, 1 plus 2 is 3. Since y is supposed to be -1, then that will not be the choice of sign. If we choose the negative value, we get 1 minus 2. The answer is -1, which would be what we want for the value of y. So we use the negative sign, and that will be our final solution. Now, we also want to know at what interval of x is this solution valid. If we plug in any value of x here, positive value, that is fine because square root of a positive number is a real number. However, if this whole term becomes negative, then we have an imaginary number which we don't want. So we just find the values of x that will make this negative and exclude that in our set of accepted values of x. We find that x should be greater than -2 because we can um, we can rewrite this expression inside the square root and simplify it to x squared plus 2 times x plus 2. This x squared plus 2 is always positive, while this x plus 2 will only be positive for x greater than -2. If x is -2, this term becomes 0, and we get a value of y equals 1. But earlier, I have mentioned that y should not be equal to 1, so we exclude that. That's why we only have x greater than -2. The integral curves for the original differential equation is shown here, shown as solid blue lines. And the valid solution would be that when the interval for x is only those x greater than -2, shown by this. The solution with the boundary, using the boundary condition y at 0 equals -1 is in this black curve, but we exclude -2 and 1 because in this case, we don't want y to be equal to 1. So the solution, these are the integral curves, the blue solid lines, solid curves for different values of arbitrary constant or the integration constant c. But for a specified boundary condition, the solution is this black curve, except for this point -2 and 1. And it's only valid for x greater than -2. So as it the trend is it goes to -2, it then turns back, or it then would reach a hit a tangent line and then goes back to points greater than -2.